The sun rises for everyone. Gravity pulls the same way. 2 plus 2 equals 4, no matter who counts. Facts. Absolute, unbreakable facts that no serious person disputes. Then 6 photons ran a test on that certainty in 2019, and absolute truth failed by 5 standard deviations. And every experiment since has only made the violation worse. Not a glitch, not an error in the equipment. The failure of absolute truth is a measured property of the universe. Quantum mechanics, the most successful theory physics has ever produced, does not just allow 2 observers to disagree about what happened. Quantum mechanics requires the disagreement. But the problem did not start in 2019. A physicist named Eugene Wigner posed a thought experiment in 1961, and nobody could resolve the contradiction without breaking physics. Locality was the first assumption tested. Locality broke. Non-local realism broke next by 3.2 standard deviations in a separate lab. Self-consistency collapsed. Every escape route that physicists proposed over 6 decades, from locality to realism to self-consistency, was closed by a different result. Whether objective reality survives is no longer the question. The evidence has already delivered that verdict. A harder question has taken the place of the old one, and no physics textbook has been willing to answer the harder question. What kind of universe remains when the assumption of a single, shared truth is experimentally dead? Now, before we unpack the evidence, I want you to know this investigation is stronger with your voice in it. Subscribe, engage in the comments with what you think, and help us build the most thoughtful community in science commentary. And the first draft of that script was written in Princeton, New Jersey. The year is 1961. The scientific world rides the high of the atomic age, confident that the laws of physics stand solid, predictable, and objective. We have split the atom. Scientists have harnessed the power of the nucleus. Our belief holds that we understand the fundamental building blocks of reality. But in a quiet office at the university, the Nobel laureate Eugene Wigner writes a paper that will act as a slow-acting poison to that confidence. Wigner feels dissatisfied with the standard explanation of quantum mechanics. He sees a hole in the theory, a gap where the observer stands. To demonstrate the gap, he constructs a scenario that appears deceptively simple. He imagines a laboratory, completely isolated from the rest of the universe. Inside this laboratory, he places a friend. The friend, a competent observer, a scientist capable of making a measurement and recording a result. The context of the moment matters. In 1961, physics felt triumphant. We had mapped the subatomic world. Researchers were building reactors and rockets. Such a prevailing mood suggested one of mastery. We assumed that we simply uncovered the pre-existing machinery of the universe, a clockwork system that ran whether we observed the system or not. But Eugene Wigner stood among the few who saw the cracks in the foundation. Wigner realized that the mathematical formalism of quantum mechanics, the very equations that allowed us to build the bomb, contained a contradiction. These equations worked perfectly for atoms. However, the mathematical laws refused to tell us where the atom ended and the observer began. Wigner sat in that Princeton office and decided to push the logic to the breaking point. His decision was to put a human being into the equation. The setup follows a precise structure. Inside the laboratory, a friend intends to measure a quantum system, perhaps the spin of a silver atom or the polarization of a photon. Let us say the friend measures the spin of an atom. The particle enters the device in a superposition of spinning up and spinning down. According to the rules of quantum mechanics, until a measurement occurs, the atom occupies both states simultaneously. Activating the sensors, the friend initiates the test. Once the magnets engage, the atom chooses a path. Peering at the screen, the observer sees a flash of light. "Spin up!" the friend records. For the person inside the room, the measurement concludes. The probability has collapsed into a single, definite fact. The universe inside the box holds steady. But Eugene Wigner stands outside the laboratory, and the contradiction marks the beginning of the trouble. Wigner also qualifies as a scientist. He also follows the laws of quantum mechanics. And the Schrödinger equation, the fundamental law that governs how quantum systems evolve, is linear. This linearity means that if the atom was in a superposition and the friend interacts with the atom, the friend must also enter a superposition. From the perspective of Wigner standing outside the sealed door, the laboratory does not contain a friend who is seen spin up. Instead, the laboratory contains a friend suspended in a ghostly mixture of having seen spin up and having seen spin down. The measurement has not happened. The collapse has not occurred. The friend, the device, and the atom all hang in a quantum twilight. The scenario carries a name: the paradox of Wigner's friend. The thought experiment challenges the very concept of objective reality. Imagine a coin spinning on a table. While the coin spins, the metal appears as a blur of heads and tails. If you slam your hand down on the coin, you force the object to become one or the other. You create a fact. But what if you are the coin? To the friend inside the box, the hand has already slammed down. The result shows heads. But to Wigner, the entire room, the friend, the table, and the coin still spins. Who holds the truth? Does the coin show heads, or does the coin continue spinning? These possibilities cannot both hold true. If the friend holds the truth, the superposition collapsed. If Wigner holds the truth, the superposition persists. The contradiction exposes a flaw in our understanding of the world. We assume that facts are absolute. We assume that if a tree falls in the forest, the tree falls regardless of who hears the crash. But Wigner showed that in a quantum universe, the fact of the tree falling might belong only to the person standing under the branches. To a distant observer, the tree might be both fallen and standing. The paradox suggests that no view from nowhere can be found. No single, godlike perspective captures the entire truth of the universe. Only internal perspectives and external perspectives survive, and these viewpoints do not match. The implications feel disturbing. If Wigner holds the truth, then reality no longer functions as a solid stage where we all act out our stories. The cosmos becomes a fractured mosaic where one observer's reality and another observer's reality might not align. The friend inside the lab possesses a distinct history. Wigner outside the lab possesses a different history. And until the door opens, until Wigner steps inside and interacts with the friend, those histories stay contradictory. The universe can sustain two opposing truths at the same time, provided the truths are isolated from each other. The state is not solipsism, where only one mind operates. The state is solipsism with rules. The laws of physics work for everyone, but the facts the laws produce might stay private. Skeptics might argue that the friend feels big and warm and biological, and therefore cannot sit in a superposition. Critics might appeal to decoherence. The mechanism is the standard defense. The argument follows a specific path. The friend does not operate in isolation. The friend breathes air. The observer radiates body heat. The friend interacts with billions of environmental particles every second. These interactions carry information away from the friend, effectively measuring the state and forcing a collapse. The air molecules know the result. The walls know the result. Therefore, the environment destroys the superposition long before Wigner makes a move. But this defense fails. The argument misses the point Wigner intended to make. Wigner is a theoretical physicist. He knows about air molecules. In his thought experiment, the laboratory is perfectly isolated. The isolation includes the air, the walls, and the photons. From the perspective of Wigner, the environment inside the box just becomes part of the larger superposition. The atom entangles with the detector. The detector then entangles with the friend, who in turn entangles with the air molecules. The superposition does not disappear. The blur just expands. The quantum state spreads like a contagion. Unless a specific physical law dictates that superpositions stop at a certain size, Wigner must use the math to describe the entire laboratory, friend, air, and all, as a single quantum wave function. Decoherence explains why we do not see superpositions in daily life, but the mechanism does not explain how superpositions vanish. Decoherence sweeps the problem under the rug, but Wigner pulled the rug back. The failure of decoherence forces us to confront the measurement problem directly. The problem is the smoking gun of quantum mechanics. We know how quantum systems behave when we do not watch the particles. The systems evolve as waves of probability. We know how systems behave when we look. The waves snap into particles of certainty. Such mathematics does not tell us what constitutes a look. Think of the measurement as a chain of dominoes. Imagine the first domino as the atom. The atom sits in a superposition. The atom hits the detector, the second domino. Imagine the detector triggering first. We could argue the machine collapses the wave, or we might conclude the apparatus simply becomes entangled with the atom. The signal then travels to a computer, which displays a photon on a screen. If the screen fails to trigger the collapse, the light reaches the retina of the friend. We must ask if the eye, or perhaps the neurons of the brain itself, serves as the final barrier. But here is the central question. Where lies the cut? The boundary carries the name the Heisenberg cut, and the line is the most elusive frontier in science. The border moves depending on who you ask. John von Neumann, the mathematical genius who formalized much of quantum theory, followed this chain all the way to the end. The thinker did not shy away from difficult logic. He possessed a mind that operated with the precision of a computer. Von Neumann looked at the physical chain of measurement, including the lens, the retina, and the optic nerve, and he saw only atoms. He saw only physical systems governed by the Schrödinger equation. If the atom can sit in a superposition, then the lens must follow. Should the lens enter that state, the retina comes next. If the retina hangs in the blur, then the neurons in the brain cannot escape. Von Neumann argued that since every physical system consists of quantum particles, none of the physical parts can trigger the collapse. Such physical components just get added to the growing superposition. The only element not described by quantum mechanics, von Neumann argued, is the abstract consciousness of the observer. Our mind. He suggested that the collapse happens only when the information registers in a conscious mind. Physicists call the hypothesis the consciousness causes collapse theory. The idea feels elegant, consistent, and completely unprovable. But Wigner took the logic a step further. If consciousness causes the collapse, then the friend inside the box has already collapsed the wave function. The friend possesses consciousness. So, for Wigner to describe the friend as sitting in a superposition, Wigner must deny the consciousness of the friend. He must treat his friend as a mere physical apparatus, a collection of atoms that can be smeared out across probabilities. The logical necessity creates the solipsism trap. To save quantum mechanics, Wigner must assume he is the only true observer in the universe. Everyone else amounts to a mere mechanism. Now, the scenario felt like more than just a thought experiment, but the paradox endures. If the friend collapses the state, the equation fails. If the equation holds, the friend did not collapse the state. The pieces do not fit. We face a stark choice. Either quantum mechanics breaks down for large-scale phenomena, or our understanding of facts fails. Let us look at the cut again. Imagine you watch a video recording of an experiment. On the screen, a scientist measures an electron. You see the scientist smile and give a thumbs up. The measurement concludes. But you watch a recording. The pixels on your screen follow the laws of quantum mechanics. The light traveling to your eyes is quantum. A chilling question emerges regarding whether the scientist on the tape sits in a superposition until you watch the video. Skeptics might wonder if the past stays undecided until the moment you play the recording. The suggestion sounds like madness. We want to believe that the past is fixed. We want to believe that the scientist really did smile, whether we watch the video or not. But the Wigner's friend paradox suggests that the fact of that smile belongs only to the scientist. For you, the viewer, the smile emerges only when you engage with the information. This realization leads to a terrifying possibility. Maybe no cut separates the quantum from the classical. Maybe the superposition never ends. The possibility is the many worlds interpretation. In this view, the friend sees spin up and the universe splits. One branch contains the friend seeing up, another branch contains a copy of the friend seeing down. Wigner, standing outside, interacts with both branches. No collapse occurs. Only an infinite branching of reality persists. The friend is not in a superposition of up and down. Two friends occupy two different worlds, and Wigner is about to become two Wigners. The interpretation solves the paradox by destroying the concept of a single universe. But let us assume we want to keep a single universe. We want to occupy one world, not a billion. If we reject many worlds, and we reject the idea that Wigner is the only conscious being, we reach the uncomfortable conclusion that facts are subjective. A fact is not a property of the world. A fact is a property of the interaction between a system and an observer. The spin of the atom is not up. The spin is up relative to the friend, and relative to Wigner, the spin stays undefined. The discovery brings us to the crucial checkpoints of our investigation. We need to define our terms before we move to the hard evidence. We must define the nature of an observer. In the original thought experiment, the observer was a human being. The element adds a layer of complexity because humans appear messy, biological, and opinionated. But in physics, an observer does not need to possess a doctorate. An observer is anything that extracts information from a system and stores the data in a memory. A photon hitting a camera sensor counts as an observation. An atom leaving a track in a cloud chamber constitutes an observation. The universe fills itself with observers. Every rock, every dust mote, every beam of light that interacts with another particle performs a measurement of sorts. If we strip away the biological baggage, the paradox becomes even sharper. Let us replace the friend with a single photon. We can call this light particle the friend photon. The photon interacts with the system photon. The friend photon records the state of the system by changing the polarization. Now we possess a very simple observer. We can control this observer. Researchers can isolate the particle. We can perform interference experiments on the system. Physicists can test the radical idea of Wigner in the real world. We do not need to lock a graduate student in a box. We just need to master the behavior of light. The stakes here feel absolute. Our investigation asks if a bedrock to reality can be found. We search for truths that hold true for everyone, everywhere, all the time. If the answer is no, then science itself requires a rethink. Science relies on the idea that we uncover an objective world. We measure the mass of the electron, and we assume that mass stays the same for every observer. We assume that if we both measure the electron, we will agree. But the Wigner's friend paradox suggests that our agreement does not come guaranteed by the universe. Our agreement results from us interacting with each other. We align our realities by talking, by sharing data, by observing each other. Reality is not a pre-existing territory we explore. Reality is a consensus we build. Consider the dream analogy. When you dream, the world feels real. You see a door, you open the handle, a room appears. The room feels solid, but the room did not come into being before you opened the door. Your mind created the room in the act of perceiving the space. The paradox of Wigner suggests the waking world might function on a similar mechanism, but with stricter rules. The room shows up because you look at the walls. The shared vision might arise because the room possesses an objective existence. Alternatively, the agreement holds because when we look at each other looking at the space, we become entangled with one version of reality. Our minds lock each other into a shared hallucination of stability. The universality of quantum mechanics holds the key to this lock. If quantum mechanics is universal, if the laws apply to everything from atoms to apples to astronauts, then no escape from the logic of Wigner can be found. If a limit appears, if a scale surfaces where quantum mechanics breaks down and classical physics takes over, we should have found the limit by now. But we have not found the boundary. Extensive efforts have built larger and larger quantum systems. Researchers have put large molecules into superposition. Scientists have put vibrating membranes into superposition. The boundary keeps receding. The evidence suggests that the universe is quantum all the way up. And if the universe is quantum all the way up, then Wigner had reason to worry. No facts can survive without observers. The crossroad marks where the philosophy ends and the experiment begins. For 50 years, the Wigner's friend paradox was just a story told in coffee shops and lecture halls. The paradox served as a ghost story for physicists. Professors would warn that we might realize we do not truly know what reality means. But technology has finally caught up with imagination. Our labs can now build the laboratory Wigner imagined. Physicists can create the friend. We can seal the box. And we can check if the friend really sits in a superposition. The evidence we're about to examine comes from a series of breakthrough experiments performed in the last decade. These are nuts and bolts, laser and lens experiments. These tests have taken the question posed by Wigner and turned the philosophy into a laboratory test, and the answer does not match what we wanted to hear. The answer suggests that Wigner had reason to worry. The fracture he saw in 1961 is real. We hold our suspects. Our team holds the friend who claims the world is definite. We have Wigner who claims the world is a blur. Mathematics supports Wigner, and our intuition screams that the friend must hold the truth. To solve this case, we must look at the photons themselves. We must look at the proof. To find the answer, we must leave the blackboard and enter the laboratory. We must travel to the Heriot-Watt University in Scotland. There, a team of researchers built a machine to test reality. They created 4 observers, Alice, Bob, Charlie, and Debbie, out of beams of light. They forced these observers to disagree on the state of the world, and the team measured the degree of that disagreement. What the researchers found destroys the idea of observer-independent facts. The facts of the world do not wait to be found. The facts emerge from the act of looking, and different observers can produce different facts. Our foundation stands. The paradox is clear. The comfortable idea of a single shared reality faces trial, and the discovery leads us to the witnesses who saw the contradiction unfold. The investigation moves from the chalkboards of Princeton to the laser-dampened tables of the Scottish University's Physics Alliance. The year marks 2019. At Heriot-Watt University in Edinburgh, a team of experimental physicists led by Massimiliano Proietti decided to stop wondering if Wigner held the truth and started building a machine to prove the hypothesis. Their lab sprawls as a forest of mirrors, lenses, and nonlinear crystals, all bathed in the sterile glow of monitors. These researchers were not looking for a new particle or a distant star. These scientists were hunting for the death of objective reality. The team realized that the nearly 60-year-old thought experiment of Eugene Wigner could finally face trial using the high-precision tools of modern quantum optics. To understand the weight of this moment, we must look at the people behind the lasers. Massimiliano Proietti and his colleagues, including Alessandro Federici, operated at the absolute edge of what is physically possible. The Heriot-Watt facility ranks among the few places on Earth where 6-photon entanglement can hold controlled with enough stability to survive an entire measurement cycle. In the decades following the original 1961 paper by Wigner, the paradox lingered as a ghost in the machine of physics. Everyone knew the math worked, but nobody knew if the universe would actually allow such a blatant contradiction to occur in a real laboratory. The Heriot-Watt team spent months calibrating the equipment, fighting the thermal noise and the microscopic vibrations that threatened to collapse a quantum state before the data can register. The setup amounted to a masterpiece of forensic engineering. Rather than using a single photon, the team employed 6. These 6 photons were divided into 3 entangled pairs, each serving a specific role in a cosmic drama. The central pair acted as the system being measured. 4 remaining photons took the roles of the observers, Alice, Bob, and their respective friends. By using light particles as the observers, the team could ensure the perfect isolation that Wigner required. A human friend in a box suffers the leaks of body heat and breath, but a photon in an optical fiber is a silent, cold, and perfect witness. Effectively, the researchers were building a miniature version of the entire universe inside a few square meters of laboratory space. The mechanical heart of this machine relied on 3 separate Sagnac-type interferometers. These devices use a counter-propagating loop of light to create entangled pairs with incredible precision. Inside each Sagnac loop sits a periodically poled crystal. The Scottish team employed potassium titanyl phosphate, or KTP crystals. Periodic poling involves creating precise alternating layers of ferroelectric domains within the crystal lattice. This internal structure compensates for the inherent dispersion of light, allowing the wavelengths to hold in phase over longer distances. When a high-energy pump laser strikes these crystals, a single photon of higher energy splits into two photons of lower energy, each carrying exactly half the original power. This process, called spontaneous parametric down conversion, creates the entanglement. By precisely controlling the temperature and the orientation of the KTB crystal, the researchers ensure that the two daughter photons emerge in a state of perfect shared identity. To suppress higher-order emissions, the Scottish team had to quadruple the pulse rate of the laser through a process called temporal multiplexing. Higher-order emissions amount to noise, photons that would ruin the delicate 6-photon coincidence counting. Without this level of control, the signals from the 4 different observers would vanish in a sea of random flashes. Imagine a crime scene where 4 detectives are called to testify. 2 detectives, Charlie and Debbie, stand inside the house. Alice and Bob, the other 2 detectives, watch the house from a hill through binoculars. Charlie and Debbie look at a light on the wall and see that the bulb shows green. For the observers inside the house, the result constitutes a hard fact. But Alice and Bob, looking from the outside, perform a complex measurement on the entire house. Through the binoculars, the outside observers do not see a green light. Instead, the exterior witnesses see a house that sits in a superposition of green and red. The Scottish experiment aimed to force these 2 groups of witnesses into a courtroom to see if the individual testimonies could ever reconcile. Inside the lab, the mechanism relied on what physicists call a fusion gate. The device functions as the soul of the photonic observer. When 2 photons enter the gate, the particles interact in a way that allows one photon to extract the state of the other without destroying the quantum information. That physical interaction constitutes the measurement. One photon acts as the friend, storing the memory of the spin or polarization in the physical state of that photon. The other photon is the system. A polarizing beam splitter at the core of the fusion gate performs a logic operation between these 2 particles. The interaction is a non-destructive process, meaning the gate does not absorb the photons to interpret the state. Instead, the gate forces the system photon to change the phase of the friend photon. Now the friend photon carries the information about the system in the very cycle of the wave. Once the friend photon settles on this phase, the system counts as technically measured. In any normal version of reality, the measurement should mark the end of the story. The wave function should collapse. The truth should stand fixed. But here is the thing. The Scottish team then performed the super-observer measurement. Alice and Bob, acting as the Wigner figures, used a series of beam splitters and half-wave plates to perform what scientists call a Bell state measurement on the friend and the system together. That measurement offers a way of asking the universe if the friend holds a superposition. If the friend had truly collapsed the wave, Alice and Bob would see a random series of results. But if Wigner held the truth and the friend quantified as a quantum system, Alice and Bob would see a specific pattern of interference. The results would show that even though the friend had seen a definite fact, the outside observers could prove that no such fact ever existed. Data began to pour in over 360 hours of continuous measurement. The researchers were looking for a violation of a specific mathematical limit called a Bell-Wigner inequality. This inequality marks a boundary. If the universe holds objective, the data must land below the number 2. If the data crosses that line, the assumption of observer-independent facts dies. As the 6-photon coincidence counts grew, the signal began to climb. The researchers watched as the numbers moved from 1.9 to 2.0 and then surged into the forbidden territory of 2.4. The surge did not amount to a fluke. The Heriot-Watt team calculated the statistical significance of the result. In science, we use a metric called sigma to measure how likely a result turns out as a mistake. A 3 sigma result signals a hint. A 4 sigma result signals a discovery. but the Scottish team reached 5 standard deviations of confidence. That level of precision is the gold standard of physics. A 5 sigma result means the chance of the data being a random coincidence sits at only 1 in 3.5 million. To put the data in perspective, a person holds better odds of being struck by a meteorite while clutching a winning lottery ticket than for the result to be a mistake. The photons were screaming the truth. Absolute reality does not exist. The weight of this finding cannot be overstated. Our investigation reveals a laboratory where Charlie and Debbie have recorded a definite result. These friends possess a fact in the memory of each observer. But Alice and Bob possess a fact stating that Charlie and Debbie possessed no such memory. Both facts come backed by 5 sigma evidence. This situation constitutes the ultimate scientific nightmare. The scientific method relies on the idea of reproducibility. If a researcher measures the temperature of water at 100 degrees and another researcher measures the same water, both must agree. If a disagreement occurs, the assumption suggests that one person holds the wrong answer. But the Scottish photons prove that both groups can hold the truth, even when the accounts flatly contradict each other. The truth is fractured into a collection of relative perspectives. This discovery forces a radical re-evaluation of the human place in the cosmos. We used to think of the observer as a passive recipient of information. We thought the world was a movie, and we stood as just the audience. But the Photonic Witnesses suggest that the observers are the projectors. We do not just discover the world, we create the world through the act of relationship. The death of absolute truth marks the birth of a relational universe. If a 6-photon system can disagree on reality, then the idea of a single objective block universe amounts to a convenient myth we tell ourselves to preserve sanity. The rock of reality has turned out as a cloud of possibility that only hardens when we engage with the substance. The fracture of fact moves the investigation from a single experiment to a broader logical trap. If the Heriot-Watt data holds true, the world faces more than a weird quirk of light. Our team looks at a fundamental boundary on what researchers can know. To map this boundary, the investigation must look at the work of Kokwei Bong and the colleagues of that researcher at Griffith University in Australia. In 2020, Bong and the team published a paper that pushed the Wigner paradox into a final, most lethal form. These researchers realized that the contradiction between Wigner and the friend amounted to more than a simple disagreement. The conflict was a no-go theorem, a logical dead end, a proof stating that a person cannot have a cake and eat the cake too. To understand the Bong no-go theorem, imagine the universe as a game of cards with 3 strict rules. Rule number 1 is locality. Nothing can travel faster than light. If a card changes in London, the card in New York cannot change instantly. Information must travel across the space. Rule number 2 is no superdeterminism, the belief in free will for scientists. Researchers can choose which measurement to perform without being manipulated by the universe. Rule number 3 is the absoluteness of observed events, or IOE, the common sense belief that if an event happens, the event happens for everyone. If a light turns red, the light holds red for the entire world. For centuries, science has operated as if all 3 rules hold true. We assume the world was local, that we possessed free choice, and that facts were absolute. But the Griffith University team, building on the work of Kassler Bruckner, proved that these 3 rules are mathematically incompatible with quantum mechanics. If a person wants to keep the laws of quantum physics, that person must kill one of the rules. A choice must occur regarding which part of reality a person feels willing to sacrifice. A local world is possible, but the facts will turn relative. Absolute facts are possible, but the world will turn non-local and spooky. Or both persist, but the person must accept that free choice is an illusion controlled by the beginning of time. The math behind this realization involves the derivation of 9 inequivalent classes of Bell-type inequalities, encompassing 932 facets. These are more than simple equations. These are multi-dimensional boundaries in a space called the local friendliness polytope. Think of this polytope as a complex, faceted diamond. If the correlations between the observers land inside the diamond, the world holds objective. But if the data points land outside even one of the 932 facets, the foundation of absolute reality crumbles. The Griffith team used specialized software called Panda to map these facets. They searched for any configuration of the four observers that would force the universe to choose between locality and truth. The theorem amounts to a much stronger version of the famous Bell's theorem from the 1960s. John Bell proved that the universe cannot be both local and real in the sense of having hidden properties. But Bong and the team showed that the problem reaches deeper than hidden properties. The problem reaches into the very events observers see with their own eyes. Bell dealt with the unseen. Bong deals with the seen. The local friendliness theorem proves that even the most basic facts of experience, the clicks of a detector or the flashes of a screen, form part of this logical breakdown. At the heart of the Griffith experiment was a proof-of-concept version of the extended Wigner scenario. The team used a pair of entangled photons, but the researchers added a clever twist. The scientists used the path of the photon as the friend. In this setup, the photon makes a choice between two different tunnels in an interferometer. The choice of path is the observation. If the photon goes left, the friend has seen left. If the photon goes right, the friend has seen right. Because the path of the photon is a physical state the researchers can control, the team could treat the path as a memory. A series of beam displacers and half-wave plates created a controlled path measurement, effectively putting the friend into a box made of light. The team then applied the interrogation of the 932 facets to the data. Researchers were asking the photons more than one question. Scientists were asking the particles the same question from many different angles, looking for a single slip-up. The goal was to test if the correlations between Alice, Bob, Charlie, and Debbie could find an explanation in any theory that kept all three rules intact. The result gave a resounding no. Data violated the inequalities. The local friendliness of the universe proved to be a lie. The pieces do not quite fit, and the universe seems to choose the most radical path. Most physicists feel unwilling to give up locality. Believing in faster-than-light magic is not an option for most. Most scientists feel unwilling to give up no superdeterminism. We want to believe that researchers control the experiments. That situation leaves only one target for the axe, the absoluteness of observed events. The Griffith experiment suggests that the rule to sacrifice is the very idea that a single objective reality exists. The world faces a forced acceptance that the truth is a local phenomenon. An event can hold true for Charlie, but untrue for Alice. Think of this as a relativity of fact. Albert Einstein showed the world that time and space are relative to the speed of the observer. If a person moves fast enough, the clock of that person slows down compared to the clock of another. The idea was shocking in 1905, but the world has grown to accept the concept. GPS satellites now must account for this time difference every day. But Bong and Proietti show a relativity that Einstein never imagined. These researchers show that the very contents of time and space are relative. This relativity dictates more than the timing of an event. The physics determines whether the event happens at all. The shared story is what physicists call effective objectivity. The world feels solid because decoherence works so fast and so broadly that the relative differences vanish. Imagine a swarm of 1 billion bees. From a distance, the swarm looks like a single solid object. You can see the shape, you can track the movement. But as you get closer, the solid object dissolves into 1 billion individual parts. Each bee does something different. Solidity of the swarm is an illusion created by the distance. Our classical world is the swarm. Quantum mechanics is the individual bee. Wigner and his friend were the ones who realized that the swarm is not a single entity. The no-go nature of the theorem means no middle ground exists. Finding a clever way to keep absolute facts and locality together while keeping quantum mechanics proves impossible. The math is a locked door. If the goal is to keep the most successful theory in human history, the idea of a view from nowhere must die. Humanity must accept that the universe is a collection of first-person accounts with no third-person narrator to settle the score. This existential implication is the most humbling realization in modern science. Centuries have gone into trying to find the objective laws of the world. Humanity wanted to find the ultimate ledger of the cosmos. But the Photonic Witnesses and the Griffith theorem suggest that the ledger holds empty until a person writes in the pages, and different writers can write different stories in the same book. The universe is not a finished product. The cosmos is an ongoing creation, a participatory event where the act of looking becomes the act of making. As we move forward in this investigation, the mystery only deepens. If facts are relative, how far does this relativity go? If a photon can disagree with another photon, can a human disagree with another human? The investigation must ask if the Heisenberg cut is just a convenient fiction. If no objective facts exist at the quantum level, where do the objective facts of daily realities originate? How does a world of relative shadows produce a world of solid stone? This question brings us to the debate between the two most prominent interpretations of the data. On one side, we find relational quantum mechanics, championed by Carlo Rovelli. Rovelli argues that physical variables like position and velocity do not exist in isolation. These properties work like the velocity of a train. A train does not possess a velocity in an absolute sense. A train only possesses a velocity relative to the track or relative to another train. Rovelli suggests that the entire universe consists of these relations. On the other side, we find QBISM or quantum Bayesianism. This view, led by Christopher Fuchs, goes even further. QBISTs argue that the wave function is not a physical entity at all. The wave function is just a mathematical tool that an agent uses to track personal expectations. When a measurement happens, the agent does not collapse a physical wave. The agent simply updates a personal ledger based on new information. In this view, reality is fundamentally relational. The cosmos is also deeply personal. Each observer carries a private world, and the objective universe is just the area where those private worlds happen to overlap. The clues point toward even stranger territory. The investigation must look at the nature of time itself. We must examine if the actions of the present can reach back and rewrite the history of the past. If reality does not hold fixed until a measurement occurs, then the past might be just as flexible as the future. This possibility brings us to the most controversial experiment in the history of light, the delayed choice quantum eraser. The test will show the world that the fact of what happened yesterday might not face a decision until tomorrow. The investigation into the death of reality is about to turn the gaze of the detective toward the erasure of time. This transition from space to time reveals a universe that is fundamentally relative and unfinished. We find that the solid world is a temporary agreement, a fragile consensus that a single, well-placed measurement can dissolve. Forensic evidence from the Scottish and Australian labs has provided the smoking gun. Objective reality is more than just missing. The evidence suggests that absolute reality never existed to begin with. Humanity has existed in a relational web, unaware that the strands emerge from the observations of the dwellers. The next step of our journey will take the investigation into the heart of this temporal dissonance. We will look at how information can face destruction after that information has already registered. We will see how the universe can unmake a fact, and we will confront the possibility that history is not a track we follow, but a story we constantly revise. The investigation into the Photonic Witnesses has cleared the way for a much deeper, much more disturbing question. If the past can face erasure, then what holds of the truth? The concept of a fixed and unchangeable past is the anchor of the human experience. We rely on the assumption that an event, once recorded by the universe, remains etched in the absolute bedrock of history. But the investigation now enters a territory where the timeline itself becomes fluid. This investigation moves from the laboratory floor to the grand scale of the cosmos, to ask a question that feels like a violation of common sense. Can a decision made in the present change the history of the past? This mystery was first proposed by the legendary physicist John Archibald Wheeler. In 1978, during a symposium at Princeton University, Wheeler presented a thought experiment that would haunt the scientific community for decades. The room at Princeton was filled with the sharp scent of chalk dust and the low murmur of skeptical peers. Wheeler stood before a massive slate blackboard, his hands covered in white residue as he sketched out a reality that seemed to defy the flow of time. Wheeler was a man who saw the universe not as a collection of cold objects, but as a participatory event. He famously argued that every physical entity at the deepest level has an immaterial source, that all of physics springs from yes or no questions, from binary choices, from bits. But the most disturbing contribution of Wheeler was the realization that the quantum choice of an observer could reach back through time. The context of the proposal from Wheeler demands a look at the state of physics in the late 1970s. The world had accepted that quantum particles could exist in superpositions. We knew that a photon could behave like a wave or a particle depending on the experiment, but Wheeler realized that the timing of the experiment was the real anomaly. He proposed a version of the double-slit experiment where the choice of how to measure the photon is delayed until after the photon has already passed the slits. In the 1978 lecture, Wheeler described a great smoky dragon to represent the quantum system. The tail of the dragon is the source of the photon. The mouth of the dragon is the detector where the photon lands. But the body of the dragon is a cloud of smoke. We know where the dragon starts and where the dragon ends, but the middle is a mystery. Wheeler argued that the dragon only takes a definite shape when we look at the head. And if we look at the head in a specific way, we force the tail to have always been a specific way, even if the tail happened billions of years ago. The mechanical heart of this mystery is the Mach-Zehnder interferometer. This device is the courtroom where the timeline of reality is interrogated. Inside the interferometer, a single photon strikes a beam splitter. This half-silvered mirror forces the photon into a superposition. The photon now travels along two different paths simultaneously, path I and path B. These paths are separated by distance, often several meters in a lab or millions of light years in space. At the end of the journey, the two paths meet at a second beam splitter. This result proves that the photon traveled both paths at once. The photon behaved resembling a wave. The history of the photon is a both-path history. But the anomaly appears when we remove the second beam splitter. If the second beam splitter is absent, the two paths do not interfere. Instead, the photon simply travels to one of two detectors. This result provides path information. We now know that the photon traveled either path A or path B. The photon behaved resembling a particle. The history of the photon is a single-path history. The genius of the proposal from Wheeler was the timing. He suggested that the observer could wait until the photon has already passed the first beam splitter and even traveled 99% of the distance before deciding whether to put the second beam splitter in place. If the observer waits until the last nanosecond to insert the mirror, the photon is forced to have traveled as a wave for the entire journey. If the observer leaves the mirror out, the photon is forced to have traveled as a particle for the entire journey. The choice in the present moment dictates the nature of the event that happened in the past. Imagine a traveler standing at a fork in the road. The fork is like the first beam splitter. In a normal world, the traveler chooses the left path or the right path. This choice is a fact of history. But in the quantum world of Wheeler, the traveler does not choose. The traveler exists in a ghostly superposition of both paths. The traveler is a cloud of smoke moving through the forest. The traveler only becomes a solid person when a detective at the end of the forest decides how to look for the footprints. If the detective uses a wave detector, the traveler is forced to have always been a wave that took both paths. If the detective uses a particle detector, the traveler is forced to have always been a single person who took one path. The detective sees more than the footprints. The detective is creating the footprints in the past by the way the detective watches the present. The analogy suggests that the universe is like a game of 20 questions where the answer is not decided at the start. The answer is slowly created by the questions we choose to ask. The mystery here is the violation of the temporal sequence. We expect the cause to precede the effect. We expect the path to be chosen before the arrival. But Wheeler proves that the arrival determines the path. This realization led to the most grand-scale version of the experiment, the cosmic delayed choice. Wheeler proposed using a distant quasar as the light source. A quasar is the glowing center of a galaxy billions of light years away. As the light from the quasar travels toward Earth, the light passes a massive galaxy in the foreground. The gravity of the foreground galaxy acts as a gravitational lens, splitting the light of the quasar into two paths that bend around the galaxy. These two paths travel for billions of years before reaching a telescope on Earth. When the light arrives, a researcher in a lab decides how to measure the photon. If the researcher uses an interferometer, the researcher forces the photon to have traveled both sides of the galaxy for 10 billion years. If the researcher uses a particle detector, the researcher forces the photon to have traveled only one side. The decision made in a laboratory in 1978 reaches back 10 billion years to dictate the path of a photon that started the journey before the Earth even existed. The existential implication is a complete breakdown of the block universe model. We tend to think of time as a completed movie reel. The past is already filmed. The present is the frame we are currently watching. But Wheeler suggests that the movie is being filmed and edited in real time, and the editor can change the opening scene while the ending is playing. This possibility means that the history of the universe is not a solid record. The history of the cosmos is a participatory process. We exist as more than passengers in the universe. We are helping to define what the universe was. The Great Smoky Dragon of Wheeler is a reminder that reality is a conversation between the observer and the observed. And the most disturbing part of the conversation is that we can change the beginning of the story by the way we choose to listen to the end. To expand our understanding of this temporal rewrite, we must look at the precision of the modern laboratory. John Wheeler understood the logic, but he lacked the tools to see the dragon in high definition. The modern investigator has no such limitation. We who built interferometers that stretch for kilometers, we have synchronized atomic clocks that can measure the passage of time to within 1/quintillionth of a second. These tools allow us to see that the delay in the choice is more than a trick of the mind. The delay is a physical fact that the universe must respect. If we wait until the last possible moment to insert the second beam splitter, the photon responds with the same resemblance to wave interference as if the mirror had been there since the beginning of time. The universe maintains a state of perfect flexibility until the final bit of information is extracted. This realization that the past is flexible moved the investigation from a thought experiment to a physical reality. In 1999, a team at the University of Maryland led by Yoon-Ho Kim and Yanhua Shi decided to turn the Smoky Dragon of Wheeler into a laboratory fact. The team was working with a concept called the quantum eraser, an idea first proposed by Marlon Scully and Kai Drew in 1982. Widely considered one of the most elegant and confusing tests in the history of science, the Maryland experiment posed a single question. Could the path information be erased after the photon had already been recorded? Kim and Shi used entangled pairs of photons to create a system where one photon acts as the witness for the other. This setup allowed the researchers to manipulate the memory of the past without ever touching the primary photon. The engineering core of the Kim experiment lies in the geometry of the entanglement. The lab used a pump laser to strike a barium borate crystal, a non-linear optical material similar in function to the KTP crystals used in Edinburgh. Through spontaneous parametric down conversion, a single ultraviolet photon from the laser enters the crystal and interacts with the atomic lattice of the material. The interaction split the original photon into two infrared photons. These two photons are entangled twins. They share a single quantum identity. One twin, called the signal photon, travels toward a detector named Detector 0. The other twin, called the idler photon, travels into a complex maze of beam splitters and mirrors. We watch the signal photon. Meanwhile, the idler photon carries the secret of the path. The distance to detector 0 was kept much shorter than the distance through the idler maze. This difference in distance meant that the signal photon was always recorded first. The idler photon was still wandering through the maze when the signal photon had already finished the journey. The laboratory setup involved 4 different idler detectors, named Detector 1, 2, 3, and 4. Detectors 3 and 4 were the path detectors. If the idler photon landed in detector 3, the researchers knew with 100% certainty that the photon had taken path I. If the idler photon landed in detector 4, the researchers knew the photon had taken path B. This knowledge is the path information. When this knowledge exists, the entangled signal photon at detector 0 behaves resembling a particle. No interference pattern appears. The history of the photon is fixed. But detectors 1 and 2 were the erasers. These detectors were placed after a final beam splitter that scrambled the information. When an idler photon landed in detector 1 or 2, identifying the path was impossible. The memory of the path was physically destroyed. The path information was erased. The anomaly in the data was the timing of this erasure. Because the signal photon at detector 0 was recorded first, the signal should have already decided what to be. The signal photon was measured 8 nanoseconds before the idler photon even reached the final beam splitter. In the world of high-speed electronics, 8 nanoseconds is an eternity. This duration is enough time for light to travel over 2 meters. By the time the idler photon was being erased or marked, the signal photon was already a recorded pulse of electricity in the computer memory. The fact of the behavior of the signal photon should have been settled history. But the data from the Kim experiment showed something impossible. When the researchers looked at the signal photons that were later matched with erased idlers, an interference pattern appeared. The signal photon, which had been recorded as a random scatter of points, suddenly revealed a wave structure. But the signal photons matched with path idlers remained resembling a particle. Imagine a photographer taking a picture of a mysterious stranger. The stranger is wearing a mask. A click of the shutter captures the moment and the camera goes away. Just like that, the event is over. The past is recorded. But then, a detective in another city finds the stranger and decides whether to take the mask off. If the detective moves the mask, the original photograph in the pocket of the photographer suddenly changes. The face of the stranger becomes clear in the old photo. If the detective leaves the mask on, the old photo remains blurry. The choice made by the detective in the second city after the photo was taken dictates the content of the image that was already captured. In the Maryland lab, the idler photon is the detective. The signal photon is the photograph. The choice of the idler to land in an eraser detector or a path detector changes the history of the signal photon that was already registered in the computer. The mystery here is how the signal photon knows what the idler photon will do in the future. Both photons are entangled, but they are separated by space and time. At detector 0, the signal photon arrives and is recorded. Only later does the idler photon reach the beam splitters that decide the fate of the information. The Kim experiment proves that the universe does not decide the nature of a past event until the information about that event is finalized. If the information remains hidden or is erased, the past remains in a state of resembling a wave superposition. If the information is revealed, the past collapses into a resembling a particle reality. This result suggests that history is not a sequence of events. History is a sequence of information states, and if the information can be scrambled after the fact, the history can be rewritten. This rewrite of the past requires us to look even deeper into the Heisenberg cut we identified earlier. We are seeing that the cut is more than a boundary in space. The cut is a boundary in time. Information is the thread that binds the present to the past. If we cut the thread through erasure, we release the past from the obligation to be definite. The universe maintains a library of possibilities, and the books are only printed when the reader turns the final page. This participatory nature of time is what Wheeler meant by a smoky dragon. We can touch the tail, and we can touch the head, but the body of the dragon remains a mystery until the final measurement occurs. This realization that the past is an information state led the investigation to the final, most disturbing logical trap. If the Maryland lab proves that we can erase the past of a single photon, what happens when we try to describe the entire universe this way? This question brings us to the work of Daniela Frauschiger and Renato Renner at the ETH Zurich. In 2018, these two researchers published a paper that shook the foundations of quantum logic. The paper carried a title that amounted to a declaration of civil war within physics, asserting that the quantum framework cannot consistently describe observers who apply the same framework. Frauschiger and Renner used a modified version of the paradox of the friend of Wigner to show that if quantum mechanics is universal, different observers will arrive at contradictory facts that are both true according to the math. The logical engine of the Frauschiger-Renner paradox is a multi-agent reasoning chain. The setup involves 4 agents named Alice, Bob, and their 2 friends, Friend 1 and Friend 2. These agents are more than abstract points in an equation. Alice is a meticulous researcher in a high-precision optics lab. Bob is a theoretical physicist in a separate, equally isolated facility. They are separated by miles of optical fiber. The experiment begins with Friend 1 tossing a quantum coin. This coin is a spin particle in a superposition. Depending on the outcome, Friend 1 prepares a second particle and sends the particle to Friend 2. Friend 2 then performs a measurement. This part of the experiment is the first layer of reality. Friend 1 and Friend 2 have facts. They have seen the coin land and measured the particle. They record the results in their logbooks. For them, the world is definite. But then Alice and Bob, the super observers, perform measurements on the entire laboratories of the friends. Alice measures the lab of Friend 1, Bob measures the lab of Friend 2. These super observers are looking for the interference patterns we saw in the Maryland lab. They are treating the friends, the logbooks, and the entire buildings as quantum systems. The logical anomaly here is the if-then chain of reasoning. Frauschiger and Renner showed that if we follow the standard rules of quantum mechanics, we can build a series of perfect logical deductions. Agent Alice observes a specific result and concludes with 100% certainty that Bob must observe a specific result. Bob, in turn, concludes that Friend 1 must have seen a specific coin flip. Friend 1 concludes that Friend 2 must have seen a specific particle spin. But when we follow the chain to the end, the conclusions clash. The deduction of Alice says that Bob must see result X. But the measurement of Bob shows result Y. Both Alice and Bob have used the exact same laws of physics. Both have performed the measurements of the agents perfectly. But the facts they derive about the world are flatly contradictory. One agent predicts a 0% probability for an event that the other agent observes with 100% certainty. This disagreement is not a matter of opinion. This disagreement is a mathematical necessity of the theory. The researchers in Zurich have shown that the universe cannot maintain a single, consistent story when the observers themselves are part of the measurement. Imagine a group of 4 witnesses at a car accident. Witness 1 is inside the car. Witness 2 is on the sidewalk. Witness 3 is watching from a nearby building. Witness 4 is watching from a satellite. Witness 1 says the light was green. Witness 2 uses logic to prove that Witness 1 must have seen a red light. Witness 3 uses the data to prove that Witness 2 is correct, but the car never even existed. Witness 4 looks at the satellite feed and sees that the light was green, red, and blue at the same time. In a normal world, we would say some witnesses are lying or mistaken. But in the Frauschiger-Renner paradox, the witnesses are the laws of physics. The mistake is not in the observation. The mistake is the assumption that a single, objective story can describe the experiences of all observers. The logic of the universe is not self-consistent when the logic describes agents who are themselves part of the system. The mystery here is the failure of the view from nowhere. We have spent centuries trying to find a master perspective that can reconcile all individual accounts. We wanted an I view of God regarding the cosmos. But Frauschiger and Renner proved that such a view is mathematically impossible if quantum mechanics is universal. If the laws of physics apply to everything, including the observers, then those observers are trapped in a web of relative truths. There is no overarching ledger that can hold the absolute facts of the coin toss. The fact of friend 1 is not the fact of Alice. The past of the idler is not the past of the signal. The universe amounts to a patchwork of private observations with no guarantee that those accounts assemble into a single, coherent narrative. This failure of universal logic is the deepest insight of our investigation. We are finding that the contradiction we saw in the Princeton office of Wig is a fundamental feature of the cosmos. The universe does more than allow for different perspectives. The universe requires them. No single objective background exists to provide a baseline for truth. Instead, the world is a patchwork of interactions, a mosaic of facts that are only true relative to the observer who witnesses them. If Alice and Bob disagree, both are correct within their own frames of reference. The quest for a single absolute truth is revealed to be a search for something that the mathematics forbids. The existential implication of this logical fracture is the death of the single world hypothesis. Frauchiger and Renner argue that we are forced to give up one of three core beliefs. Either quantum mechanics is not universal, meaning the physics breaks down at large scales, or the world has many branches, as the many worlds interpretation suggests, or, finally, we must accept that facts are purely personal. If we choose the final path, we must accept that reality is relational. The truth is not an intrinsic feature of the cosmos. The truth is a bond forged in the encounter between a particular observer and a particular system. This realization is the ultimate investigator nightmare. This outcome means that the deeper we dig for the evidence, the more we find that the evidence depends on the shovel we are using. The investigation into the erasure of the past has led us to a place where time, history, and logic are all revealed to be fluid. We have seen that a decision today can rewrite the quasar path of 10 billion years ago. We have seen that a photon in Maryland can scramble the memory of the signal twin. And we have seen that the most rigorous logic of Zurich leads to a world where two people can look at the same event and see two different, equally valid truths. The pieces of the puzzle do more than fail to fit. Instead, those pieces seem to belong to different puzzles entirely. Our case has led to a stark conclusion. The truth is not a record we find. Reality is a story we are still writing, even as the ink from yesterday remains wet. This transition from a world of fixed facts to a world of relational events is the final threshold of our investigation. The death of absolute reality is not an end. The death of reality is the beginning of a much deeper understanding of our role as the authors of the cosmos. The investigation has proven that the past bends to the present and that logic fractures when observers describe each other. But one final refuge remains for the believers of a real world. For decades, physicists clung to the hope that objects carry hidden properties connected across space by invisible, faster-than-light threads. Non-local realism was the last sanctuary. The idea that the universe is spooky, but still fundamentally solid. The next step of this case will test that sanctuary with a precision tool built in Vienna, and the result will leave nowhere left to hide. The sanctuary was built on a single, desperate assumption. After the experiments of Edinburgh and Griffith demonstrated that facts are relative and that observers can record contradictory truths, the defenders of an objective world retreated to one final position: non-local realism. The argument followed a clear logic. Yes, the universe allows spooky connections. Yes, particles can coordinate their behavior across infinite distances at speeds that violate the limit of light. But beneath this spookiness, the physical world is still real. The polarization of a photon, the spin of an electron, the position of an atom, these properties exist before anyone measures the systems. The spooky connections simply coordinate the results without creating the properties from nothing. Accepting the weirdness of the quantum world was tolerable, as long as the foundation of the world remained solid. For decades, this compromise was the preferred escape hatch of mainstream physics. When Bell proved in 1964 that the universe cannot be both local and real, most physicists chose to sacrifice locality. Faster-than-light correlations were strange, but the strangeness was manageable if the particles still carried real properties. A pair of entangled photons could be imagined as two radios tuned to the same secret station. The broadcast was instant, the synchronization perfect, but the music was real. The song existed inside the radios before anyone pressed play. But here is the complication. The escape hatch was built on a flaw. The compromise of non-local realism had survived for nearly 4 decades without serious challenge. Physicists treated the position as a permanent safe harbor, a place where the strangeness of quantum correlations could be absorbed without abandoning the core conviction that particles carry real properties. The comfort of this position blinded the community to a subtle vulnerability hiding inside the mathematics. In 2003, the physicist Anthony Leggett began to dismantle non-local realism from the inside. This Nobel laureate of the University of Illinois possessed a reputation for finding subtle gaps in established theories. Where most physicists had accepted the binary choice presented by Bell, the theorist saw a third question hiding beneath the surface. Bell had asked whether the universe is local and real. The experiments proved the answer was no. But the deeper question was whether the universe could be non-local and still real. Could spooky action save the concept of pre-existing properties? The theorist suspected the answer was no. More than a question of how information travels, the fundamental mystery was whether the information exists at all before the moment of detection. To test this suspicion, the physicist derived a new mathematical inequality, a boundary line that any theory respecting non-local realism must obey. The derivation required a shift in how researchers examined correlations between entangled particles. Bell had tested measurements in a single plane. The new approach demanded measurements across multiple non-orthogonal planes. Elegant and severe, the logic left no room for ambiguity. Each model assumed that each photon carries a definite polarization vector, a fixed arrow pointing in a specific direction. This vector could be influenced by non-local parameters, meaning the measurement choice of Alice could instantly affect the outcome recorded by Bob. The concession gave the realist position every possible advantage. Faster-than-light communication was permitted. The universe was free to be as spooky as the universe desired. But the inequality demanded that particles still carry a well-defined angular momentum when those particles emerge from the source. The demand was the definition of a pre-existing state, and the theorists suspected that the very concept of a definite state was the true problem, not the speed of the communication. The core of the model rests on 3 specific assumptions. First, physical realism, the belief that observation outcomes follow from properties carried by physical systems before any measurement occurs. Second, physical states are statistical mixtures of subensembles possessing definite polarization. Third, these subensembles obey the law of Malus, a fundamental rule of optics describing how the intensity of a polarized beam of light decreases when passing through an ideal polarizer. Specifically, the law states that the transmitted intensity is proportional to the square of the cosine of the angle between the polarization direction of the beam and the transmission axis of the polarizer. By insisting that any non-local theory must still respect this basic optical rule, the derivation constructed a logical trap from which objective reality could not escape. Imagine 2 radios separated by 100 miles. These radios always play the same song at the same time. We might conclude that a hidden, faster-than-light wire connects the 2 devices. But the crucial part of this model is that the song exists. The music is a real property of the broadcast, even if the broadcast is spooky. So the new inequality was designed to test if the music of the quantum world is a pre-existing broadcast, or if the song is being composed in the moment the radio is turned on. The measurement tool for this final test was a high-precision photonic laboratory at the University of Vienna. In 2007, a team led by Simon Groblacher and Markus Aspelmeier, working under the guidance of Anton Zeilinger, decided to put the inequality to a direct experimental trial. The Vienna facility ranked among the most sensitive optical laboratories on the planet. The vibration of a passing car or the heat from a single lamp could ruin the data. Researchers used spontaneous parametric down conversion to create pairs of entangled photons from a 2 mm thick crystal of beta barium borate, pumped by a frequency-doubled titanium sapphire laser producing pulses lasting only 180 femtoseconds. A femtosecond is 1/4 of a second. This incredibly short pulse was necessary to ensure that the timing of every photon creation was precise enough to survive the statistical analysis. The experimental challenge facing the Vienna team was substantially harder than a standard Bell test. In a Bell experiment, a visibility of roughly 71% is sufficient to prove non-locality. Any noise in the detectors or misalignment of the mirrors would have dropped the visibility below threshold, concealing the truth behind a curtain of statistical uncertainty. The team compensated for the birefringence of the crystal, which causes different polarizations to travel at different speeds through the material, using additional crystals and half-wave plates to keep the entangled photons perfectly synchronized. Inside the lab, half-wave plates and quarter-wave plates rotated the polarization of the photons into 3 different planes on the Poincare sphere, a mathematical representation of all possible polarization states, where points on the equator represent linear polarization and the poles represent circular polarization. By measuring across these different orientations, the team could test whether the correlations obeyed the limits predicted by a non-local realist theory or shattered those limits in accordance with pure quantum mechanics. The critical distinction between this test and a Bell test was precisely this requirement to measure in multiple orthogonal planes. Bell had only examined correlations in a single dimension. The new inequality demanded a 3-dimensional investigation of the full sphere. Piezoelectric motors nudged optical components into position with an accuracy of 1/10 of a degree. Silicon-based avalanche photodiodes detected the arrival of every single photon, converting the faintest flash of quantum light into an electrical pulse that the computers could register. An atomic clock synchronized the detectors to ensure that recorded coincidences were genuine events, not random noise. Every stray reflection, every thermal fluctuation in the crystal, every vibration from the building had to be identified and suppressed. The margin for error was vanishingly small. A single misaligned mirror or a temperature drift of half a degree in the crystal could shift the data below the threshold of detection. These investigators were not simply counting flashes of light. Those researchers were counting the very moments when the universe chose a state. Data from the Vienna laboratory proved devastating for the realist position. Correlations between the entangled photons surged beyond the limits that any non-local realistic theory could explain, crossing the boundary defined by the inequality and reaching a value consistent only with the predictions of pure quantum mechanics. The violation was measured at 3.2 standard deviations. While 3.2 sigma falls below the 5 sigma gold standard that particle physicists typically demand for a discovery, the implications were arguably more lethal than any Bell test ever conducted. The Bell experiments had killed the idea of a local reality, and the Groblacher experiment killed the idea of realism. Consider the distinction between these two results carefully. Locality says that distant events cannot influence each other faster than light. Realism says that objects possess definite properties whether or not anyone measures those properties. Bell proved that a person cannot have both. Most physicists chose to keep realism and sacrifice locality, accepting a spooky world where particles communicate across the void, sharing secrets at speeds that dwarf the pace of light. But the Vienna experiment proved that even this sacrifice was not enough. The spooky communication is real. The particles are indeed connected across space, but the properties those particles share are not pre-existing. The properties are created in the moment of detection. No broadcast carries the song. Instead, the music is a composition, written in real time by the instrument and the listener together. For decades, theorists like David Bohm had argued that we could keep realism if we just added a pilot wave that guided the particles non-locally. Bohm proposed that every particle possesses a definite position and momentum at all times, but these properties follow the guidance of a non-local quantum potential that responds instantly to changes across the cosmos. This pilot wave theory was the most sophisticated version of the spooky radio model. However, the work of Groblacher proved that even the pilot wave cannot save pre-existing properties. The Vienna data violated the boundary that any realistic theory must respect, regardless of how much non-local assistance the theory receives. If the guiding wave exists, the wave must be steering an entity that has no definite state. The pilot wave can push and pull, but the object being guided carries no fixed identity to push or pull against. The hidden variables are more than just concealed. Those variables are non-existent. The most generous version of reality, a version given every advantage, every loophole, every spooky shortcut, still failed the test. Imagine a library where every book sits blank on the shelf. When a visitor walks into the building and pulls a volume from the stack, words appear on the page. The visitor examines a story about a king and shows the book to a colleague. Both observers agree that the volume is real and the king is a fact. But if both visitors return the book to the shelf and leave the building, the words vanish. The story of the king does not reside in the library. The story emerges from the act of examination. In the quantum world revealed by the Vienna experiment, polarization is the story, the detector is the visitor, the vacuum is the library, and the shelves remain always blank until someone chooses to open a cover. The mystery here is how a world of blank books can produce a world of solid stone. We do not experience a universe that vanishes when we turn our heads. We experience stubborn consistency. This consistency is the reason we clung to realism for so long. Rejection of pre-existing properties feels like a betrayal of our senses. But the 3.2 sigma violation is a physical measurement of the limits of the real. The spooky action that Einstein feared is only half of the story. What completes the picture is that the action is not acting on anything that was already there. Every recorded property is the creation of the measurement. Now, I wanted to believe that the investigation could stop here. We have found the smoking gun in the laboratory of Vienna. We have seen that the ledger of reality is blank. But the mystery has one final, deeply personal layer. If the properties of a photon do not exist until a detector measures the particle, what about the measurer? What about us? This question brings us to a psychological and logical deadlock that threatens to dissolve the very idea of a shared world. We are confronting more than the death of the object. We are facing the fragmentation of the truth. This fragmentation connects every thread of the investigation. The Wigner paradox showed that two observers can disagree on the state of a system. Proietti and Bong confirmed this disagreement with 5 sigma confidence. The delayed choice eraser of Kim demonstrated that the past remains flexible until the final piece of information is settled. And the inequality tested in Vienna proves that the disagreement runs deeper than hidden properties that the observers simply cannot see. The properties do not lurk in concealment. No hidden layer of reality waits beneath the surface for a clever enough instrument to uncover. The pieces of the puzzle do not fit because the pieces do not exist until we attempt to assemble the picture. The existential weight of this conclusion is the total rejection of the philosophical anchor that the human species has gripped for centuries. We want to believe that the floor stays beneath our feet when we close our eyes. We want to believe that the moon hangs in the sky whether or not anyone looks at the glowing surface. But the 3.2 sigma violation suggests that these certainties are not properties of the cosmos. These certainties are products of a massive, ongoing conversation between every particle in the universe, a conversation that produces the illusion of solidity. If facts are relative, why do we not see people walking through walls or cars appearing and disappearing in traffic? The answer lies in the scale of this conversation. Our world appears objective because we are all constantly measuring each other, locking each other into a shared consensus by the very act of existing in the same space. Consistency at the macroscopic scale is not evidence of an objective background. Rather, this apparent stability is a symptom of decoherence operating at a speed and scale so vast that the relative differences between observers vanish before anyone can notice. A single grain of sand interacts with roughly 10 to the power of 23 air molecules every second. Each interaction is a measurement. Each measurement locks the grain into a definite position relative to the surrounding environment. By the time a human eye registers the grain, trillions of prior measurements have already forced the quantum possibilities into a single, stable outcome. The solidity we experience is not a property of the grain. The solidity is the accumulated weight of countless observations performed by the environment long before we arrive. Think of a massive multiplayer video game. Each player has a local computer. Each computer renders the world from a slightly different perspective. When two players look at the same mountain, both computers calculate the same polygons and textures. But no central screen exists. Only the individual perspectives of the players exist, synchronized by the network of interactions. The quantum universe revealed by the experiments of Wigner, Bell, and Groblacher suggests that the physical world operates on this same principle. Mutual observation is the only constant in a universe where the objects are blank until examined. And so the master ledger we spent centuries searching for turns out to have been empty all along. Non-local realism has fallen alongside local realism. The investigation has destroyed the last refuge of the objective world. And the question that remains is what replaces the void left behind when the objects dissolve? The answer, emerging from the work of Carlo Rovelli and Christopher Fuchs, will force us to abandon the very concept of a thing and confront a universe that is purely relational, a web of connections with no center and no edge, where the act of looking is the act of making. The investigation into the missing reality now enters the most radical phase. We have stripped away the certainty of the past and the stability of the object. We have witnessed the erasure of time and the fragmentation of the testimony of the photons. Our journey reveals a universe that appears as a collection of fractured perspectives, a mosaic of facts that refuses to assemble into a single picture. To make sense of this mess, our team must look at a proposal that emerged in 1996 from the mind of Carlo Rovelli. Rovelli represented a theoretical physicist who suspected that the current measurement problem stems from a fundamental mistake: the assumption that the state of a physical system remains absolute. Relational quantum mechanics, or RQM, represents a theory that suggests physical states do not exist as properties of objects themselves, but instead function as relations between systems. The theory asks the investigator to abandon the idea of an observer-independent state of the world. In the view of Rovelli, the question of what an electron performs right now remains as meaningless as asking how fast an airplane moves without specifying a reference point. If a person sits on the airplane, the velocity of the vehicle stays at 0. If a person stands on the ground, the velocity reaches 500 miles per hour. Both statements hold true, but neither statement represents an absolute fact about the airplane. The velocity only emerges as a relation between the craft and the observer. RQM argues that every physical variable, position, momentum, spin, and even the existence of an atom follows this same relational rule. This conceptual shift was born from a moment of historical tension in the 1990s. The scientific world celebrated the 10th anniversary of the discovery of the top quark, and the search for the Higgs boson entered a fever pitch. But beneath the surface of these triumphs, a group of theorists felt the foundations of physics rotting. The measurement problem became a wall that no one could climb. Carlo Rovelli, working alongside Lee Smolin and other pioneers of loop quantum gravity, realized that the problem did not reside in the math of the atom, but in the language of the observer. They met in quiet offices at the University of Pittsburgh and the Centre de Physique Théorique in Marseille, searching for a way to reconcile the quantum world with the relativity of Einstein. They realized that Einstein had already solved half of the puzzle by making time and space relative. The next logical step focused on making existence itself relative. The mechanical deep dive into RQM reveals a universe where physical properties only happen during interactions. Think of the spin of an electron as a secret shared only during a handshake. If the electron does not shake hands with the detector, the electron possesses no spin. The property does not stay hidden. The property remains non-existent. The measurement marks the act of creation. Researchers detect these relations by measuring the correlations between two intact particles. When Alice measures her particle, she does not uncover a pre-existing state. She establishes a relationship. The numerical data from Bell tests, which we examined in previous acts, provides the proof of this relational nature. The violation of the inequalities shows that the correlations stay too strong to find an explanation through private, hidden properties. The particles coordinate their stories in real time. Ravelli found inspiration for this idea in the deep history of philosophy, reaching back to the pre-Socratic thinker Anaximander. Anaximander suggested that the world does not consist of things, but of changes and relationships. QM applies this ancient wisdom to the subatomic world. To understand this conceptual shift, consider the analogy of the color of a fruit. Imagine a world where every piece of fruit appears as a dull gray until someone looks at the object. When a person picks up an apple and examines the skin, the apple turns red. For the observer, the redness represents a solid, undeniable fact. The observer might call a friend on the telephone and tell the friend that the apple shows red. But until the friend actually sees the apple or hears the voice, the fruit remains gray in the world of the friend. The property of redness does not belong to the apple. The redness emerges from the relationship between the observer and the fruit. This universe contains no colored apples. Our world consists of the interactions that produce the sensation of color. QM suggests that the entire physical world operates on this principle. The floor stays under the feet of the traveler because the traveler interacts with the floor. The moon stays in orbit because the gravity of the Earth represents a constant measurement of the position of the moon. Information in this context marks an event defined by physical correlation between systems. When Alice measures an electron, Alice gains information. From the perspective of Alice, the wave function has collapsed. But a second scientist named Bob, observing Alice and the electron, must describe the entire room, Alice, the detector, and the electron as a single, complex superposition. For Bob, no collapse has occurred. RQM insists that both Alice and Bob hold correct views. The fact feels real for Alice, but the fact does not yet exist for Bob. The realization causes a psychological whiplash. This shift means that the solid world we inhabit resembles a web of gossamer threads rather than a pile of bricks. The shared world we experience does not represent a pre-existing stage. The shared world marks a massive, ongoing conversation between every atom in the cosmos. We agree the sun hangs in the sky because we all constantly measure the sun and each other. The universe represents a collection of interactions that produce the illusion of objects. No thing resides at the center of the relation. The pieces do not fit because researchers keep looking for the physical gear when the scientists should study the motion. But this investigation must now shift from the relation between systems to the mind of the investigator. Quantum Bayesianism, or QBISM, led by Christopher Fuchs, goes even further. QBISTS argue that the wave function does not represent a physical thing at all. The wave function serves as a mathematical tool that an individual agent uses to calculate personal degrees of belief about the future. Following the logic of Bruno de Finetti, probability does not exist as a solid object like a tree or a rock that a person might bump into. Instead, probability represents an estimate inside the head of the agent. When a scientist calculates the spin of an atom, the researcher does not measure a property. The scientist sums up personal history and expectations. This redefines the Born rule. The rule does not represent a law of nature, but functions as a normative rule for consistent gambling. If a researcher believes the spin shows up, the Born rule guides the betting strategy. The quantum world represents a casino where the house always wins unless the gambler uses the math. The mechanical deep dive into QBISM reveals that the collapse of the wave function marks just an update of a personal ledger. Imagine you watch a horse race. Before the gates open, you possess a probability for every horse. You might think the favorite possesses a 50% chance of winning. The estimate represents your wave function. When the race ends and the favorite crosses the line, your probability collapses to 100%. The horse did not physically change from a probability wave into a solid animal at the finish line. Only your information changed. QBISM argues that the entire universe works this way. The state of an atom marks just the best guess of the scientist. We detect this by looking at how researchers change their predictions based on new data. The anomaly reveals that different researchers, starting with different beliefs, will eventually converge on the same facts if they share enough data. The math of Photonic proved that subjective beliefs can produce objective agreement. Christopher Fuchs describes every measurement as an act of creation. The observer does not stand as a passive recipient of a pre-existing world. Instead, the agent represents a participant who forces the universe to make a choice. Think of a weather forecast. A 70% chance of rain does not represent an objective fact about the atmosphere. The rain represents an event, but the probability exists in the head of the person holding the umbrella. QBISM avoids the paradoxes of Wigner because the facts of Wigner belong to Wigner, and the facts of the friend belong to the friend. These agents exist in the same world, but these agents do not share the same state of information. Quantum theory succeeded because researchers abandoned the hunt for hidden clockwork and instead mapped the precise limits of human intervention. Quantum mechanics represents the manual that tells the user exactly how much the user can know before the universe pushes back. We do not just watch a movie, we help write the script. This synthesis brings us back to the legendary John Archibald Wheeler and the concept of existence from bit. Wheeler suggested that every bit of existence derives from the apparatus, elicited answers to yes or no questions. The evidence has shattered the blocked universe model. The past, present, and future do not exist simultaneously in a solid block. The block resembles more of a fluid reshaped by the act of observation. No objective background exists. Only the network of fact creations remains. This network operates like gossip in a small town. The history of the town exists in the stories residents tell each other. If everyone agrees the old oak tree faced a strike by lightning in 1950, then the event represents a fact for that town. The tree does not need a physical scar for the lightning strike to stay real. The tree only needs the consensus of the observers. The objects we see represent the gossip of atoms. The mystery deepens when we ask why this gossip stays so consistent. If everyone dreams their own world, why do the dreams match? The answer resides in the swarm of bees effect. When two systems interact, they become entangled, they share a story. If Alice talks to Bob, their realities synchronize. Alice tells Bob, the apple shows red. Bob looks at the apple. Because they have interacted, the apple now shows red for both. This process spreads through the environment at the speed of light. The spreading marks decoherence. Every photon bouncing off the apple and hitting a wall tells the wall that the apple shows red. The environment becomes a massive distributed memory. The objective world marks just the area where so many stories have faced sharing that the contradictions stay buried under a mountain of agreement. The swarm looks solid because we stay too big to see the individual bees. The consistency of the macroscopic world does not occur because the world stands solid. The consistency emerges because the observers all constantly tell the same story to each other through the exchange of photons and the pull of gravity. Gravity and light act as the messengers that synchronize our perspectives. Consider a distant crowd in a stadium. From a high vantage point, the crowd moves like a single fluid organism, a sea of color shifting in waves. But inside the stands, that unity vanishes. You see thousands of individual people, each making private choices and moving in different directions. The sea of color is an illusion born of scale and distance. Our classical world is the fluid organism, while the individual participants represent the quantum states. We synchronize our realities into a shared hallucination of stability. This shared story represents what physicists call effective objectivity. The world feels solid because the decoherence stays so fast and so vast that the relative differences vanish. The human mind wants to believe the Big Bang represents an objective fact that happened 13.8 billion years ago. But if reality requires an observer, the Big Bang stands as a fact relative to the observers looking back at the cosmic microwave background. The past represents a reconstruction based on the evidence available now. The universe was busy measuring itself, particle by particle, interaction by interaction, until the web of relations became dense enough to produce the illusion of a solid history. The Big Bang did not wait for a single-celled creature or a physicist with a doctorate before the event began to exist. The cosmos existed as an ongoing creation, a participatory event where the act of looking represents the act of making. This realization carries a heavy existential weight. If the universe possesses no objective background, then we represent the ones who breathed the smoke into existence, giving the dragon a shape where none existed before. Our choices and our relationships represent the forces that forge the reality we inhabit. The pieces of the puzzle do not fit because the puzzle undergoes constant assembly. We have graduated from the role of passive spectators. In this relational cosmos, we have become the authors of the very laws we once thought were written in stone. The quest for a single absolute truth reveals itself as a search for something that the mathematics forbids. The investigation has reached the ultimate threshold. We have seen that the clockwork universe represented a convenient fiction, a mask hiding a world where interaction remains the only true substance. The pieces of reality have dissolved into a relational web, leaving us not as passive spectators, but as the active writers of the cosmic story. This journey through the quantum void has revealed that the truth does not represent a treasure we uncover. The truth represents a relationship we build, a shared story that only exists because we possess the courage to witness the events. The death of absolute reality does not represent a void. This death marks the opening of a new frontier where we finally assume our roles as the architects of the laws we observe. Our investigation has shown that we define the world, and that the only true reality resided in the connection we share with the universe. The gaze represents more than discovery. The gaze marks a creative force that calls the physical world into being. We have looked into the abyss, and we have found that the abyss looked back, waiting for us to tell the story. The case file on absolute reality now sits open on the desk of the investigator, and the evidence gathered across this investigation appears as overwhelming as the testimony remains unsettling. Our journey began in 1961 with a thought experiment from Eugene Wigner. This Nobel laureate dared to ask if the truth of the world could split between two different observers. Wigner imagined a friend locked inside a sealed laboratory, performing a measurement on a quantum particle while Wigner waited outside. From the perspective of the friend, the particle possessed a definite state. From the perspective of Wigner, the entire room remained in a hazy cloud of probability. This paradox suggested a crack in the foundation of the physical world, a hint that the universe might not possess a single objective history. For decades, this question remained a philosophical curiosity, a ghost story for physicists to tell late at night. But in 2019, the investigation moved from the chalkboard to the laboratory. Massimiliano Proietti led a team at Heriot-Watt University in Edinburgh to test the idea. These researchers designed a state-of-the-art experiment using 6 photons to play the roles of Wigner, the friend, and the quantum system. Inside that Scottish laboratory, the air hummed with the vibration of cooling systems, while lasers carved precise paths through the dark. The researchers used entangled photon pairs to establish a set of facts that researchers could test against the requirements of an absolute reality. The goal aimed to see if the accounts of different observers could reconcile into a single, universal ledger. The results delivered a shock to the scientific community. Violating the associated Bell-type inequality by 5 standard deviations, the team pushed physics into a new reality. Such a statistical weight provides a level of certainty that researchers rarely match in the history of experimental physics. The evidence showed that the facts established by the friend and the facts established by Wigner stood fundamentally incompatible. Ultimately, the investigators proved that the pieces of the world do not fit together into a single, observer-independent framework. The mechanical deep dive into this experiment reveals a universe where information does not exist as a fixed property of an object, but resides as a relationship between systems. In the lab, the researchers used a Type I fusion gate to extract information from the photons without destroying the delicate quantum states. This interaction allowed one photon to act as a memory, storing the fact of the observation. By comparing the records of the 4 different observers in the extended Wigner scenario, The team demonstrated that the assumption of local observer independence leads to a contradiction. If we hold fast to the ideas of locality and the freedom of choice, then we must accept that the physical world stays observer-dependent. The measurement represents no discovery of a pre-existing state. The measurement represents the act of establishing a relation. The numerical data from Edinburgh acts as the primary witness in our case, testifying that the solid ground beneath our feet represents a shifting mosaic of perspectives. To understand this breakdown of objectivity, imagine two detectives examining a crime scene. One detective stands inside the room, looking at a broken vase on the floor. For this first detective, the broken vase represents a solid fact, a piece of evidence that the observer can photograph and tag. The second detective stands outside the house, looking through a window that stays covered in a thick, swirling fog. From this perspective, the room appears as a blur of possibilities. The vase might stay broken, or the vase might remain whole. Both detectives use the best tools available. Both detectives report the truth of their own observations. In our daily experience, we assume that the fog will eventually clear and that both detectives will agree on the state of the vase. But quantum mechanics suggests that the fog represents a fundamental part of the universe. For the detective outside, the vase truly remains in a state of being both broken and whole until a direct interaction occurs. No hidden truth exists behind the fog. The truth only emerges during the handshake between the observer and the observed. This analogy helps us grasp why the findings of Proietti remain so radical. Their work proved that the two detectives both hold the truth, even when the reports of the detectives flatly contradict each other. The findings of this investigation point to a profound conclusion. Observation shapes reality. We have seen how the delayed choice quantum eraser allows the measurement of an entangled twin to erase path information even after the first particle registered. The evidence suggests that the very history of a particle remains unwritten until the final observation occurs. We have also examined the violation of the inequality of Leggett in 2007, which rejected the idea of non-local realism by 3.2 standard deviations. The measurement result means that even if we allow for spooky action at a distance, we cannot save the idea that objects possess pre-existing properties. The universe refuses to face a pinning down. Evidence suggests that the physical world consists not of a collection of things, but of a network of events. These events represent the fact creations that John Archibald Wheeler described as the answers to yes or no questions. But the findings lead us to the most difficult part of the investigation. If reality consists of a collection of fractured, observer-dependent facts, then why do we all agree on the state of the macroscopic world? If the accounts of the photons can contradict each other, why can the accounts of human beings not do the same? The answer seems to reside in the process of decoherence, the gossip of the atoms that we uncovered during our descent into the quantum void. Decoherence represents the rapid and vast exchange of information between a system and the environment. Every photon that bounces off a wall, every molecule that strikes a surface, represents a tiny observer recording a fact. This deluge of information occurs with such staggering speed that any underlying contradictions immediately face obscuration by a vast consensus. The stability we experience arises from the overwhelming volume of these relationships. Existence feels firm because the exchange of information stays so rapid that any individual deviations vanish. Our senses remain too slow to catch the flickering of the quantum shadows. We perceive a solid object because we measure 1 trillion interactions at once, and the average of those interactions creates the illusion of a fixed background. The apparent solidity of the world arises because the sheer volume of environmental interactions drowns out the quantum flickering before our macroscopic senses can register the blur. A distant swarm of insects appears as a singular, unified mass, masking the chaotic and independent trajectories of the individual creatures within. Think of a digital image on a screen. If you look at a single pixel, you see a tiny, flickering dot of light that can change in a microsecond. The pixel remains isolated and unstable. But when you zoom out to see the entire screen, millions of these dots work in concert to form a steady image of a mountain or a face. The mountain does not exist on the screen, only the coordination of the pixels exists. Our macroscopic world represents the image, while quantum mechanics represents the individual pixel. We agree on the reality because our computers, our brains, and our bodies process the same collective signal. The fact of the color of the stadium results from the massive coordination of the individual agents. Our macroscopic reality works in this way. We agree the sun rises because we all lock into a shared story by the constant exchange of light and gravity. The consistency emerges from the scale of the participation. This analogy helps the investigator understand how a world of relative facts can produce the illusion of an absolute reality. The findings lead to a profound paradox. Facts stay relative, yet we all agree the sun rises. The Bong no-go theorem formalizes this tension. Published in 2020, the proof demonstrates that locality, free choice, and absolute facts stay mathematically incompatible with quantum theory. If we want to keep our belief in a shared world, we must give up the idea that events stay absolute. This realization means that a sunset represents a real event for the person watching. However, the event does not represent an absolute fact of the world that exists independently of the gaze. The truth of the sunset represents a relationship. This shift from what exists to how we interact represents the core of relational quantum mechanics, or RQM and QBISM. The shift marks a transition from studying objects to studying information. The paradox remains that the very tools we use to understand the world, our eyes, our brains, our detectors, stay as the ones that prevent us from seeing a single, objective reality. The investigation has shown that the absolute truth we chased for centuries represents a ghost. Every measurement represents a perspective, and every fact represents a relation. We detect this relational nature through the violation of inequalities that bound the correlations of an observer-independent world. This 5 sigma result from Proietti provides the proof that the ghost cannot face capture. The paradox represents no failure of our science. The paradox represents a revelation of the nature of the cosmos. In this world, the pieces do not fit together because the pieces represent no parts of a single machine. These pieces represent the individual notes in a vast, ongoing performance. We agree on the melody because we all listen to each other. The solid world represents the music produced by the interaction of the atoms. The realization causes a psychological whiplash, a shift that forces the investigator to abandon the comfort of the spectator and embrace the responsibility of the participant. This brings us to the final, and perhaps most haunting, question of our investigation. If reality requires an observer, what occurred before we arrived? If the universe represents a web of fact creations, what resided as the state of the cosmos during the billions of years before life emerged? The problem of the pre-human universe remains. Standard science tells us that the Earth formed 4.5 billion years ago, and that the first stars ignited 13 billion years ago. But if a fact only exists as a relation between an observer and a system who witnessed the birth of the first galaxy, the question challenges the very idea of a solid, linear history. If the moon only exists during the act of measurement, one might ask if the moon existed before the first eye opened. History functions as an ongoing retrieval of data, a map we draw using the information currently available to us. The ancient universe did not wait for a human witness to become real. The cosmos stayed busy measuring itself through every collision of gas and every pull of a star. This web of relations built the story of the past, one interaction at a time. The record of the Big Bang represents no absolute tape we currently play back. The record represents a reconstruction that we perform now, based on the stories that the atoms have told each other for billions of years. Imagine the universe as a massive, dark forest. Before anyone enters the forest, the trees and the animals already interact. The wind blows through the branches, and the rain falls on the soil. The interactions of the pre-human world remained constant. Each interaction represents a tiny fact, a momentary relationship. When a human walks into the forest with a flashlight, that human sees a specific path and specific trees. The human might think the forest always existed exactly as the human sees the trees. But the flashlight represents an interaction that changes the scene. The human does not see the forest as the forest exists. The human sees the forest as the human interacts with the forest. The history of the forest represents the sum of all the wind, the rain, and the light that ever touched the trees. This analogy helps us understand how the universe could exist before us while still staying observer-dependent. The cosmos existed as a participatory event long before we arrived to join the conversation. Our journey has demonstrated that the objective world represents a collective narrative, a resilient and persistent illusion of permanence fueled by the constant communication between every particle in existence. We have found that the universe consists not of things, but of relationships. We represent more than passive recipients of a pre-existing world. We forge the reality we inhabit through the very act of existing and observing. The investigation has shown that the objective world represents a shared story, a massive and ongoing hallucination of stability maintained by the gossip of a quintillion atoms. This discovery represents no loss of truth. Instead, the discovery marks a gain of connection. We breathe life into the equations, giving the dragon a shape where none existed before. Our search for a single, absolute truth turns out to be a pursuit of a shifting shadow that changes shape as we move. In this relational cosmos, the only enduring reality is the connection itself. In the relational universe, the only true substance remains the interaction. The pieces of the investigation now lie on the table, and the pattern stands clear. Our universe does not represent a machine made of matter. Instead, the universe exists as a web of information and perspective. The death of the absolute represents no void. The death of the absolute represents an invitation. We now understand that observation acts as an engine of creation, a process that summons concrete facts from a void of mathematical potential. The truth likely resides in the gap between observer and observed. Reality represents a relationship, a dialogue that has continued for 13.8 billion years. We stand as the current witnesses in this cosmic dialogue, the observers who have peered into the darkness only to find a reflection of our own gaze staring back, waiting for the next word. The ambiguity represents no problem to solve. Such ambiguity remains the very catalyst that keeps us asking questions. The investigation continues not because the truth stays hidden, but because the truth represents a narrative we undergo constructing piece by piece, observation by observation. Ultimately, the files do not stay closed. Our files just wait for the next witness to step forward. So here is what we know. The experimental evidence from the laboratory in Edinburgh proves that facts are relative to the person who observes them. But what this really means is that our reality is not a collection of fixed objects. Instead, the universe is a shifting network of relationships where we are active participants. Every time we think we have figured the universe out, the cosmos turns around and shows us we are just scratching the surface. If you want to help me improve the quality of this channel and tackle even bigger topics, consider using the donation link in the description. Every bit goes directly back into making better content for you. Your support allows the research for these investigations to continue and ensures that the production of these documentaries remains high quality. If you know someone who is obsessed with the idea that reality may not exist independently of observation, send this video their way. Sharing is the best way to help this community grow. I will catch you in the next one. Let curiosity guide you, keep learning, and know that you are always appreciated.